Welcome back to the Explainer. Today, we're doing a real deep dive system architecture review into the Agent Witness Protocol, or AWP for short. We're going to look straight under the hood at the engineering logic that makes this entire system tick. And honestly, if you're a systems or security nerd, you are going to find these architectural decisions absolutely fascinating. So, I want to start by asking you to think about a highly critical problem. Imagine an AI agent just took a major, high stakes action. Maybe it moved thousands of dollars. Maybe it generated a legally binding document, or it acted on a very specific user authorization. Later on, an auditor comes knocking and asks, what exactly did that agent do? Who permitted it? And how do we absolutely know this record hasn't been secretly altered? Now, today, you'd basically just have to trust the system's own logs, which really means trusting the system operator. But how do you mathematically prove what that AI agent did offline with zero network access and without trusting the operator at all? Well, here is our roadmap for the teardown. We'll deconstruct this in 6 quick steps. 1. Witnessing AI agent actions. 2. Composition over invention. 3. The honesty boundary. 4. Anatomy of a receipt. 5. Time and quantum defense. And finally, 6. Zero trust offline verification. All right, section 1, witnessing AI agent actions. Let's just dive right into the core problem of verifying governed AI events. So, what exactly is AWP? First off, it's really critical to understand what it isn't. It's not a tool for issuing identities or authenticating who a person really is. Instead, think of it as a binding grammar sitting on top of existing standards. It defines a single, structured, signed record of a governed agent event, meaning it captures the agent's intent, the human authorization behind it, and the actual artifacts it touched. And it always does this by hash, never by content. It creates a tamper-evident cryptographic receipt that you can verify entirely offline. Moving right along to section 2, composition over invention. Let's look at AWP's core engineering philosophy. It's built on radical candor and a pretty stubborn refusal to invent new cryptography. I absolutely love this because it brilliantly illustrates the protocol's 80-20 rule. The engineering team is completely upfront that roughly 80% of AWP is simply adopting proven commodity standards. Rather than building some bespoke, unproven crypto chimera, they're using the DSSE and in-toto standards for the signed wrapper. They adopt the strict RFC 9162 Merkle subset for transparency log inclusion proofs. They're using C2SP for signed checkpoints, and open timestamps or EDOS for time anchoring. Why? Because they work flawlessly today. But the real engineering moat, the strategic differentiator, is that remaining 20%. The value doesn't actually live in the standard envelope bytes. It lives in the payload and the topology. We're talking about a genuinely neutral third-party witness topology. You simply can't witness your own actions and claim independence, right? It also includes a typed honesty boundary, a verified human-to-agent authorization binding, and ADOS-qualified, legally recognized time paths. That is where the genuine engineering effort was spent. Okay, section 3, the honesty boundary. Let's see how this builds into what I think might literally be the most rigorous part of the entire system, structural limits on what it can actually claim. The crucial point here is that AWP enforces its limits right in the actual code types, not just hidden away in some documentation. Making an overclaim is grammatically impossible in the schema. A verification claim has to be typed. It proves integrity since witness, meaning the data is unaltered since the exact moment it was recorded. But, and this is key, it deliberately lacks the vocabulary to claim authenticity at origin. It's never going to tell you a document was legally authentic when first seen, it won't magically prove a human's true identity, and it won't prove that every single action was logged. If you try to overclaim, the verification fails instantly. I actually want to read this direct quote from the source material just to really hammer home the fierce intellectual honesty of this engineering team. They say, tamper-evident, not tamper-proof. AWP makes alteration detectable. It does not make any underlying store physically immutable. They are not trying to market this as some kind of unbreakable magic. It is strictly evidence of tampering. Section 4, Anatomy of a Receipt. Let's transition over to reverse engineering the actual cryptographic artifact itself, layer by layer. So, a full receipt basically bundles 4 chained layers into one neat, self-contained file. So literally anyone can recheck the event offline. First up, you have the signed envelope, signed by the producer's record key. Second is the transparency log inclusion proof, which shows it exists in an append-only log. Third, you've got a signed checkpoint, signed by the log's completely independent key. And fourth, the external time anchor, proving its existence in time. Now, I'm going to geek out for just a second on the transparency log layer because their design choice here is so smart. They deliberately chose to use the strict RFC 9162 raw byte Merkle rules. That means when they're hashing nodes, they decode to 32 raw bytes. They don't mess around with hex string text as UTF. Listen, if you've ever spent a weekend debugging hex to byte confusion, you know it is a massive source of interoperability bugs. It's a great way to lose your sanity. But this specific choice mathematically guarantees that off-the-shelf verifiers can interact with their log without throwing errors. Plus, those domain separation prefixes completely shut down tree extension attacks. Section 5, Time and Quantum Defense. Next, I want to pivot to how the architecture actually anticipates future threats without breaking current compatibility. What's really fascinating here is how they handle post-quantum defense. They don't just rip and replace the old cryptography. They use an additive hybrid approach. They're combining a classical Edge 25519 signature with a NIST-standardized post-quantum signature called MLDSA44. And crucially, both algorithms sign the exact same byte string. There is zero rewrite required to the underlying envelope. And because their policy demands the classical signature must always pass, an attacker would literally have to break both algorithms simultaneously to forge a receipt. And there's that radical candor again. The protocol surfaces this post-quantum edition as an experimental advisory. They explicitly refuse to market it as future-proof or unbreakable. It's just a verifiable, honest backstop that operators can opt into without risking the core protocol on a very young algorithm. That same exact honesty applies to how they anchor time. AWP supports two different paths for time anchoring, and the verifier will report the exact evidentiary weight of whichever one you use. You've got open timestamps, using Bitcoin block time. It's free, trust minimized, but asynchronous. Or you have RFC 3161, which supports paid, EIDAS qualified trust service providers if you need that auditor-grade legal compliance. The verifier won't silently overclaim. It tells you exactly which anchor backs the time and whether it actually carries qualified legal weight. And finally, Section 6, Zero Trust Offline Verification. Let's talk about the ultimate test of all this logic, putting the power directly into the hands of the auditor. Zero. That is exactly how much network access, how many APIs, and how much trust in the producer you need to verify an AWP receipt. The reference verifier is a totally open-source tool. You can put a receipt file on a USB stick, walk it over to a completely air-gapped machine, run the verification, and check every link in the cryptographic chain yourself. The development team actually does this really visceral demo to prove it. They load up a clean receipt, and the offline verifier passes all 11 checks perfectly. Then they open the text file and literally flip a single hex character in the payload. When they rerun it, the verifier instantly fails closed right at the signature check. Bam. And it doesn't just fail silently. It explicitly names the exact layer that broke. It mathematically proves tamper evidence right in front of you. Which brings us to the ultimate question for the future of governed AI. If an AI takes a critical action but leaves no cryptographic receipt, no offline verifiable proof of its intent, its authorization, and its untouched artifacts, did it really happen? Going forward, this exact engineering logic really forces us to question the baseline security of any AI system that just expects us to trust its internal logs. Thanks so much for joining me on this teardown, and I hope this architectural deep dive has given you a brand new framework for thinking about verifiable AI.